Hey everyone, Neil deGrasse Tyson here, and welcome to Knowing Info. Today we're diving into the world of engineering, but not the kind that makes you say, wow. We're talking about the oh no moments, the catastrophic failures that sent shockwaves through history. Engineering is about pushing boundaries, reaching for the unimaginable. But sometimes those ambitions come with a hefty price tag. When structures fail, lives are lost, trust is broken, and we're left picking up the pieces, trying to understand what went wrong. Join me as we explore 5 engineering disasters that shook the world, uncovering the science behind the failures and the lessons learned. From collapsing dams to disintegrating bridges and exploding spacecrafts, we'll see how these events reshape not just industries, but our understanding of risk, responsibility, and the delicate balance between innovation and safety. Chapter 1. St. Francis Dam. A concrete colossus crumbles. Our journey begins in the sun-drenched landscape of 1920s California. Picture this, a time of rapid growth, with Los Angeles thirsty for water to fuel its booming population. To quench this thirst, a colossal dam was erected, the St. Francis Dam. Towering over 200 feet, this concrete giant held back a reservoir of water larger than any other in the world at the time. It was a symbol of human ingenuity, a testament to our ability to tame nature itself. But on March 12, 1928, that illusion of control was shattered. Just before midnight, the dam crumbled. A catastrophic failure sent a wall of water 10 stories high, surging through the valley below. The torrent ripped through towns and villages, leaving a path of destruction in its wake. Over 400 lives were lost, making it one of the deadliest dam failures in American history. The aftermath was devastating, but it also ignited a firestorm of questions. How could a structure seemingly so impenetrable simply give way? The investigation revealed a cascade of errors, from inadequate geological surveys to flawed concrete mixtures. The dam's design, hailed as innovative, proved to be its Achilles heel. It relied heavily on the strength of the canyon walls to support its immense weight, a gamble that backfired tragically. The disaster exposed a critical flaw in the engineering process, the danger of overconfidence and the importance of thorough geological assessments. The St. Francis Dam collapse was a stark reminder that even the most ambitious projects can be undone by overlooked details. It led to stricter regulations, improved construction practices, and a renewed focus on the ethical responsibilities of engineers. The lessons learned from this catastrophe continue to resonate today, a solemn reminder that progress without prudence can have dire consequences. The ruins of the St. Francis Dam stand as a silent monument to the human cost of engineering failures, urging us to never forget the importance of learning from our mistakes. This tragedy forced a reassessment of dam safety standards across the globe. It underscored the need for independent review boards, rigorous material testing, and a deep understanding of the geological conditions surrounding such massive structures. The St. Francis Dam disaster wasn't just a failure of engineering, it was a failure of imagination. It highlighted the need to anticipate potential weaknesses, to plan for the unexpected, and to always err on the side of caution when the stakes are high. Chapter 2, Tacoma Narrows Bridge When Wind Has Other Plans. Let's fast forward to 1940, where a different kind of engineering marvel was taking shape. The Tacoma Narrows Bridge in Washington state. This elegant suspension bridge, nicknamed Galloping Gertie for its unusual movements in the wind, was a source of both pride and unease. From the start, the bridge exhibited a peculiar tendency to sway and ripple, even in relatively mild winds. Engineers at the time downplayed these movements, assuring the public of the bridge's stability. But on November 7, 1940, nature had other plans. On that fateful day, a moderate wind began to buffet the bridge, setting off a chain reaction that would forever change the field of bridge design. The wind flowing over and around the bridge's structure created rhythmic vortices like invisible whirlpools of air. These vortices in turn generated alternating forces on the bridge deck, causing it to oscillate, much like a guitar string being plucked. As the wind intensified, so did the oscillations, growing from gentle ripples to violent undulations. The bridge, designed to withstand static forces, was ill-equipped to handle these dynamic rhythmic forces. It twisted and writhed, its steel and concrete contorting in ways never imagined possible. The spectacle, both terrifying and mesmerizing, was captured on film, forever etching itself into engineering folklore. After an hour of this terrifying dance, the bridge reached its breaking point. With a deafening roar, the roadway ripped apart, sending chunks of concrete and steel crashing into the waters below. Thankfully, due to the escalating movements, the bridge was evacuated before the collapse, and there was only one casualty, a terrified Cocker Spaniel that refused to leave its owner's car. The Tacoma Narrows Bridge collapse was a watershed moment in engineering history. It forced a complete re-evaluation of how wind forces were considered in structural design. The disaster ushered in the field of aeroelasticity, the study of how structures interact with wind. Wind tunnel testing, once a novelty, became standard practice for bridge design. Engineers began incorporating aerodynamic features like streamlined shapes and open trusses to mitigate the effects of wind. The Tacoma Narrows Bridge serves as a stark reminder that nature's forces can be unpredictable and unforgiving. It underscores the importance of understanding not just the strength of materials, but also how those materials interact with the dynamic forces of the environment. The Galloping Gertie may be gone, but its legacy lives on in every bridge built since, a testament to the power of learning from failure and the importance of respecting the invisible forces that shape our world. Chapter 3, Hyatt Regency Walkway Collapse when Gravity Takes Center Stage. Our next stop takes us to Kansas City, Missouri in 1981. The setting, the grand opening of the Hyatt Regency Hotel, a symbol of the city's revitalization. The heart of the hotel was its atrium, a soaring space spanned by 3 suspended walkways, bustling with people celebrating a tea dance competition. On July 17, 1981, as the music played and dancers twirled, a seemingly insignificant detail in the walkway's design would lead to a catastrophe. The walkways, suspended from the ceiling by long steel rods, were meant to evoke a sense of openness and grandeur, but the design, seemingly straightforward, held a fatal flaw. The original design called for the walkways to be supported by a single set of long rods running from the ceiling through the second-floor walkway and supporting both the second and fourth-floor walkways. However, due to fabrication difficulties, the design was changed. Instead of one set of long rods, 2 separate sets of rods were used, one set running from the ceiling to the second-floor walkway, and another set running from the second-floor walkway to the fourth-floor walkway. This seemingly minor alteration doubled the load on the connection between the fourth-floor walkway and the rods supporting it. The connection, already a point of stress, was now bearing far more weight than it was designed to handle. As the crowd gathered on the walkways, the stress on this critical connection reached its breaking point. With a terrifying groan of metal, the fourth-floor walkway pulled away from its supports, collapsing onto the second-floor walkway below. The cascading walkways, laden with partygoers, crashed onto the crowded atrium floor in a horrifying tangle of concrete, steel, and human bodies. The collapse killed 114 people and injured over 200, making it one of the deadliest structural failures in American history. The Hyatt Regency walkway collapse sent shockwaves through the engineering and construction industry. It highlighted the critical importance of clear communication, rigorous design review, and independent verification of structural integrity. The investigation revealed a series of oversights and miscommunications that allowed the flawed design to be implemented. It exposed weaknesses in the peer review process and the need for greater accountability at all stages of a project. The disaster led to significant changes in building codes and engineering practices. It spurred the development of new standards for connection design, increased emphasis on load testing, and a renewed focus on the ethical obligations of engineers to prioritize public safety. The Hyatt Regency walkway collapse stands as a tragic reminder that even seemingly small design changes can have catastrophic consequences. It underscores the need for meticulous attention to detail, thorough communication, and a relentless commitment to safety in all aspects of design and construction. Chapter 4. Chernobyl, when atoms unleash their fury. From the realm of civil engineering, we shift our focus to the invisible world of atoms and the catastrophic consequences of their uncontrolled release. The year is 1986 and the location is Chernobyl, Ukraine, then part of the Soviet Union. Chernobyl housed a massive nuclear power plant, a testament to Soviet ambition in harnessing the atom's power. But on April 26th, a routine safety test at reactor number 4 would spiral into the world's worst nuclear disaster. The test, intended to simulate a power failure, was plagued by a series of human errors and design flaws. A combination of operator negligence, inadequate safety protocols, and a flawed reactor design created a perfect storm for disaster. As the test commenced, a surge of power far exceeding the reactor's capacity led to a catastrophic chain reaction. The reactor core overheated, causing a steam explosion that ripped through the reactor building, spewing radioactive material into the atmosphere. The explosion and subsequent fire released a plume of radioactive isotopes, including iodine-131, cesium-137, and strontium-90 into the atmosphere. The plume, carried by wind currents, spread across vast swaths of the Soviet Union and Europe, contaminating soil, water, and air. The immediate aftermath was chaotic. Firefighters, ill-equipped to handle a nuclear disaster, battled the blaze with heroic courage, many sacrificing their lives to contain the disaster. The true extent of the disaster, however, unfolded slowly as the invisible threat of radiation began to take its toll. The Chernobyl disaster exposed the devastating consequences of human error, design flaws, and a culture of secrecy surrounding nuclear technology. It highlighted the need for robust safety protocols, independent oversight, and transparent communication in the nuclear industry. The disaster forced a global re-evaluation of nuclear safety standards. It led to the development of new reactor designs, improved safety protocols, and a greater emphasis on international cooperation in the event of nuclear accidents. Chernobyl serves as a stark reminder of the immense power of the atom and the devastating consequences of failing to treat it with respect. It underscores the need for constant vigilance, rigorous safety measures, and a commitment to transparency in all aspects of nuclear technology. The legacy of Chernobyl is a sobering one, a reminder that even the most advanced technologies can pose significant risks if not managed responsibly. It serves as a cautionary tale, urging us to learn from past mistakes and prioritize safety in our pursuit of technological advancement. Chapter 5: Challenger, A Nation's Dreams. Up in Smoke. Our final stop takes us to the realm of space exploration, where the pursuit of knowledge and the human desire to push boundaries converged in a tragedy that shook a nation. On January 28, 1986, the Space Shuttle Challenger embarked on its 10th mission, carrying with it the hopes and dreams of a nation. Among the crew was Christa McAuliffe, a school teacher chosen to be the first civilian in space. Her presence on board captivated the nation, bringing the wonder of space exploration into classrooms and living rooms across the country. But just 73 seconds after liftoff, tragedy struck. Millions watched in horror as the Challenger, engulfed in a plume of smoke and fire, disintegrated in the clear blue sky above Cape Canaveral. All 7 crew members perished, their dreams of reaching for the stars extinguished in an instant. The investigation into the Challenger disaster revealed a complex interplay of technical failures and organizational shortcomings. The root cause was traced to the failure of O-rings, rubber seals in the solid rocket boosters, which lost their elasticity in the unusually cold temperatures on launch day. These O-rings, designed to prevent hot gases from escaping the booster joints, failed to seal properly, allowing a plume of hot gas to ignite the external fuel tank, leading to the catastrophic explosion. The Challenger disaster exposed a flawed decision-making process within NASA, where concerns raised by engineers about the O-ring's performance in cold temperatures were overruled by management pressures to maintain the launch schedule. The disaster led to a fundamental reassessment of NASA's safety culture, its decision-making processes, and its risk tolerance. It resulted in the creation of an independent safety oversight board, a renewed emphasis on engineering rigor, and a greater willingness to delay launches if safety concerns arose. The Challenger disaster serves as a poignant reminder that even in the pursuit of noble goals, safety must always be paramount. It highlights the importance of listening to dissenting voices, fostering a culture of open communication, and never compromising safety for the sake of expediency. The Challenger crew, in their ultimate sacrifice, taught us valuable lessons about the importance of humility, the need for vigilance, and the enduring human spirit that drives us to explore the unknown. Their legacy lives on not just in the annals of space exploration, but in the hearts and minds of those inspired by their courage and dedication. The Challenger disaster reminds us that progress comes at a cost, and that the pursuit of knowledge must always be tempered by a deep respect for the risks involved. It serves as a timeless reminder that even in the face of tragedy, we must learn from our mistakes, honor the fallen, and continue to reach for the stars. Chapter 6. Lessons etched in stone and steel. From collapsing dams to disintegrating bridges and exploding spacecrafts, these engineering disasters, though separated by time and technology, share a common thread. They remind us that progress is not without its perils, and that the pursuit of innovation must be tempered by a deep respect for the laws of nature and the importance of human life. These disasters, etched in stone and steel, serve as solemn reminders of the responsibility that comes with pushing the boundaries of human ingenuity. They urge us to approach engineering challenges with humility, to learn from past mistakes, and to prioritize safety in all our endeavors. What other engineering disasters fascinate or terrify you? Share your thoughts below. If you learned something new, hit like, subscribe, and ring the bell for more deep dives into the triumphs and failures that shape our world.